Today my video is rods don't contract. If you've been following my videos, you're aware that I've been working on a form of quantum general relativity, where general relativity is a subset of quantum field theory. And this is something that Einstein worked on starting in 1907, and many others have worked on since. And I have found that they've all made some faulty assumptions along the way. And one of the biggest problems is they assume that Lorentzian type special relativity is still valid, where you have length contraction and time dilation going on. Well, if you're unifying quantum field theory with general relativity, one of the first assumptions you make is that non-physical space can't contract. And it doesn't have clocks either. And we get the dimensions because they come from quantum field theory. Wavelengths and frequencies within the quantum field change. The actual dimensions and clock rates are emergent properties of the quantum field, not space. And that's where Einstein made his biggest single mistake in developing relativity. He imagined that space had physical dimensions after he claimed that space was non-physical. And then he imagined they had physical clocks. So, in the idea whether space has no dimensions, as it shouldn't, because it's not physical, it can't contract. So where in Lorentzian type special relativity does the length contraction come from? Well, one problem is light. What happens with light moving through space? Well, because the quantum field has a rest frame, light moves through the rest frame because its electric and magnetic fields are continually interacting with the rest frame, with the quantum fluctuations in the rest frame. So a photon leaves the source, it Doppler shifts its energy, it travels through the rest frame, and then it hits a detector, Doppler shifts its energy again, assuming the source and detector are both moving relative to the rest frame. And because the permittivity and permeability are uniform, and the clock rate changes are uniform at any point in space and have no directional dependence, the Michelson-Morley experiment wouldn't have anything but a null result. It was based on a bad assumption. Now, that tells us that we don't have to worry about what happens with length contraction with the photons. So what about physical bodies that are moving, if you actually have physical objects? Well, one way that we can look at that is what happens with the Bohr radius. And so this is something that each physicist that goes down this path discusses, is what happens with the Bohr radius. And first you have to note that you have to maintain the relationship epsilon mu equals 1 over c squared. The permittivity times the permeability is 1 over the speed of light squared. That's where the speed of light comes from. Permittivity and permeability are emergent properties from the quantum field, as first explicitly stated by Dickey. And then the speed of light is a secondary effect. So we always have to start with what's happening with permittivity and permeability. And then with the Bohr radius, it's normally put in terms of 4 pi times permittivity times the reduced Planck's constant squared divided by the mass of the electron times the charge squared. Now this is equal to the reduced Planck's constant divided by the mass of the electron times the speed of light times the fine structure constant, alpha, which is also equal, if you substitute the mass for the Compton wavelength, equal to the Compton wavelength divided by 2 pi alpha with the fine structure constant in the denominator. So you have each of these three terms must maintain their equalities. And that encompasses many of the most important constants in physics. And so you must somehow have either one solution, there's two solutions. One solution where they all stay constant, none of them change with relativistic effects. And we're looking for a second solution where relativistic effects change some of the constants, but these equalities remain valid. And we also have, to make things more complicated, we have to maintain the equation for the fine instruction constant, which is e squared over 4 pi epsilon h bar c. And I like to also consider natural units with that equation where you set epsilon c and h to 1. And then in that case, alpha is proportional to charge squared over 2. And that shows a complication where you can't just simply multiply alpha or charge by the gamma term. And by gamma I mean the general 1 over square root of 1 minus v squared over c squared, which is the relativistic contraction term used in special and general relativity. So here we have this alpha equals e squared over 2 relationship that has to be maintained. And by the way, I put in here that you have e squared over 2 is the integral of e dr. So we can think of the fine structure constant as the volume charge related to a unit of charge, one polarizer or one unit of charge, how much volume of space gets polarized. And that's where, at least in part, what the fine structure is, one fine structure constant. And even more complicating, there's a relationship between the electron's Compton wavelength and its rest mass. So if you vary the Compton wavelength, its rest mass must also vary. But the term is the density of the quantum field is equal to h bar times of the angular frequency omega to the 4th power minus 8 pi squared c cubed. So you have a fairly complicated relationship, and then omega in that equation is 2 pi c over the Compton wavelength. So in order to get in a frequency, you have to make that multiple. So then you have the speed of light being put back in the equation. But in this case, converting wavelength to frequency and the speed of light relativistically, you have to take into account that both the wavelength and the time change simultaneously. So that c in the wavelength and frequency multiple here is not fixed. You have two gamma terms going on. So you don't always have the relationship that wavelength times frequency equals the speed of light. It's broken in general relativity. So after all this going through, this basic solution is you can have the mass and permittivity change, which cancel each other, the mass and speed of light change, which cancel each other. And that can give you a solution. So we have one solution where we have the Bohr constant, the Bohr radius, pi, h bar, e, alpha, and the Compton wavelength are all constant, but epsilon and mu as well, mass of the electron and C, vary relativistically. So that's one solution that works. And that's the one that I'm using. In contrast, if you read some work by Dickey and Puthoff and others, they'll claim that you have to use the rest mass of the electron in the Bohr orbit calculation, that rest mass doesn't vary relativistically. But if you do that, then you have epsilon on the top, epsilon increases, which means the Bohr radius increases. So if the Bohr radius is increasing, then you have, instead of length contraction, you have length expansion. And it also means that the Compton wavelength has to increase, which means that the rest mass has to increase. So this equality is not an equality if you assume that the rest mass doesn't change. And not changing the rest mass relativistically is a violation of special relativity in itself. So this solution is invalid. Now, if you look at Einstein's solution, he instead say that C is fixed, so permittivity and permeability must be fixed, but he varies the mass of the electron. And if you reduce the mass of the electron, that means that the Bohr radius contracts, and so does the wavelength of the electron, which means that you get a three-dimensional contraction of atoms in his model, in addition to having a contraction due to space contracting. So there's Einstein's assumptions would give you twice the contraction, and one three-dimensional and one one-dimensional. So that doesn't make any sense. So instead, you could put the rest mass in here, and then the Bohr radius doesn't change, and the Compton electron wavelength doesn't change. But that basically just gives you the original solution that it's non-relativistic. So the only way for Einstein's math to work is if none of these constants change relativistically, which isn't valid. The way to do that is this solution here, where you vary the permittivity, permeability, the speed of light, and the mass, while the other constants remain fixed. And as far as I know, that's the only relativistic solution to this set of equations that works mathematically. And in addition to that, if you've followed some of my videos on are the constants fine-tunable, it should become readily apparent that there's no wiggle room for fine-tuning this. There's only two solutions, and one has no tuning whatsoever, and one has just a little bit of relativistic changes, and it only works one way. Well, anyway, I realize this is a lot more mathematically detailed than I go to in most of my videos, but it should give you some perspective on what physicists go through when we go through these problems. And there's additionally the problem that Dickey, Puthoff, others, Wilson originally, put it in terms of the dielectric constant changing rather than the permittivity. And the dielectric constant is the ratio of the two permittivities normally. But that has only served to complicate the arguments and led to some people making mistakes in their equations, or making it look like there's mistakes. So that's one reason why physicists who believe in curved space and contracting space haven't just totally given into the electromagnetic model, because of a few mistakes that have been made like these. So anyway, it's a major project to get this unscrambled, get everything right so that it all works the way it works in real natural physical law. So I hope you enjoyed this video, and if you did, please share, like, subscribe, make sure your physicist friends know about it. And I have my books for sale if you'd like to support my research. I have my 2 quantum field theory books and my book on the particle theory. And I touch on some of this in the 0-point universe, but I don't go into the final details because I'm still working out the final math in a final paper that describes everything and unscrambles everybody's mistakes. So I hope you be patient, mate. Hopefully I'll come out with that sometime later this year. Thanks for watching.